So let's do a little demonstration of this idea. We've got a little flight graph from one of the previous examples, and we can compute the clustering coefficient for any node. Let's say node 2. We're going to print the clustering coefficient for node 2, and then what we're going to do is actually randomly pick two of V's neighbors. Now, I ended up having to go a little bit crazy here, because we need to pick the neighbors without replacement, meaning that we pick one neighbor and then the second neighbor we pick has to be different from the first one. So I went out of my way a little bit and said, okay, here's what we're going to do. We're going to run through all of the neighbors of V is 2, and for each of them, we're going to stick them into an array called V index. And so instead of randomly choosing from this set, we're going to randomly choose indices from this array, and that'll make it easier to make sure we don't repeat. So D is going to be the degree of node V, and as long as that degree is greater than 1, we're going to pick a random neighbor, so that now neighbor here being chosen by its ordering from 0 to D minus 1. So V1 is the neighbor, the actual node name associated with that pick, and then we do a second pick, and this time we're going to again choose from 1 to D minus 1. We're going to add that to the pick that we already got with modulo D to make it wrap around. So this is going to make sure that we're going to pick something that is different from what we just picked. And we look up the corresponding ID. So we've got V1 and V2 are the two neighbors. We check whether they're connected, and we add 1 to the total if they are. We repeat this whole loop 1,000 times, and at each point in time, we take the total number of times things were connected, divided by the total number we tried. And I claim that it ought to be the case that this number converges to the actual clustering coefficient. So let's try it. So in this particular case, the clustering coefficient for node V is 0.3. And now let's watch what happens to the estimate. Well, certainly when there's only one sample that we've done so far, it's either going to be 1 or 0. It's not going to be very close to 0.3. But as we repeat this over and over again, you can see it's kind of settling in. Actually hit 0.3 briefly in the 40th try, but it's kind of bouncing around a little bit above 3, a little bit below 3. And the longer we run this, the kind of less it seems to be changing. 0.26, 0.27, 0.26, 0.27. Oh, it wandered up to 0.3 again, and ended up at 0.31. So if we do this long enough and repeat this enough times, what we'll find is that the number really is 0.3, but on any given run, it's going to be a little bit more, a little bit less. The longer that it runs, the more digits are going to be correct. And so in this particular case, this is a terrible approximation because it's actually not very close to the real answer, and it took us a long time to get this extremely bad answer. There's some nice mathematical tricks, like the Chernoff bound, that tells us how many times we have to do a random sample as a function of the variance of the distribution before we can get an estimate of a particular level of accuracy with a particular level of certainty. So if you want to be really careful about this, you can actually look up the Chernoff bound and apply it to figure out how many samples are needed. But for current purposes, run it as long as you can run it and hope for the best. All right, so that's really all I wanted to go over in Unit 5. And then we pick it up again in Unit 6, talking about computational complexity and its relation to social network analysis. See you then.